Hello and welcome to the Logs Solving Day 1 video. We are finally on our last unit, logarithms. Now what is a logarithm? If you take a real quick look at what we have going on up here in our last section, we dealt with things like this where we would change the base of a problem so they could both be 2 or something, cancel this out, and then start solving for their exponents. But what if we have something that can't change? So like we have 2 to the x is equal to 10. We can't change 10 into a base of 2. So we're going to use logarithms to help us solve for this x and the exponent. This is going to be very closely related to exponents, so if you ever feel like you need to go back and take a look at the exponent stuff, feel free. Just like with exponents, logs has many rules that we will be following, and we're going to spend a lot of time practicing using them just because I know we all feel a little shaky about them. So first rule is actually just a rearrangement, and we have that right here, where y is equal to log base a of x if and only if x is equal to a to the power of y. So I'm just going to point out a few vocab words that we have in here. So for instance, whatever is inside the parentheses, that is called the argument. And you didn't hear me say log a to the power of x. This is log base a of x. So it's of whatever is inside the argument. And this is going to be true if and only if you can rearrange it in this way. So the way that I help to think of this rearrangement is I think of bacon and eggs. So if we take a look at our first example, we have 2 to the x is equal to 10. So right now we have our base, our exponent, and our answer, but I want to rearrange that so it's bacon and eggs, B-A-E. So this is going to be log base 2, there's my b, with an argument of 10, and is equal to x, eggs. So this is bacon and eggs, base, answer, exponent. I also think of this as log bay, if you prefer to think of it that way. So you will hear me say the log bay rule probably more than once as we go through this video. Sorry if that's too cringy for you. But let's try this with a few other problems. So if we take a look at example 2, again, we're starting with just our exponent form or exponential statement, and we're going to change this into a statement using logarithms. So if we have, here's our base, here's our exponent, here's our answer, we want to change this into our log bay. So this will be log base 3, 5 as our answer, argument, and then t as our exponent, log bay. Or again, if you prefer bacon and eggs, that will work too. If we rearrange the others, BA, and this becomes, I forgot to write this on the last one, bacon and eggs, this will become log with a base of 1/4, that can be a fraction, that's totally fine. An argument of 6 is equal to x. So log base 1/4 of 6 is equal to x, bacon and eggs. And our next one would look like log base 7 of 2 is equal to n. So we'll just keep practicing this as much as we can. The last few examples are going in the other direction. So here we have base, answer, exponent. So base of 3 is an exponent of x, and an answer of 5. There you go. Let's try it with our next one. Bacon and eggs, or a base of 2, an exponent of 3, and an answer of y. So 2 to the power of 3 is equal to y, or 8 is equal to y. And then in our last one, we can say that 10 to the power of 1/2 is equal to x, or we also know that we can rewrite that as the square root of 10 is equal to x. So this is practicing using our rearrangement rule or log bay rule in both directions. So let's keep learning a few more rules. So this next page has a lot of problems on it. Normally, I would have you do this as a class. It takes maybe 3 to 5 minutes to do the whole thing. I'm just going to skip around so I don't have to do the whole thing. But what I did want to point out is that the common logarithmic function is a base of 10. So if you see this, that's base of 10. If you see a log without a base, we assume that is a base 10. So like your calculator, if you just put in log, it assumes it's a base 10. But the cool thing about that base 10 is if I'm going to call them big base and little base. If your big base, or whatever's inside the argument, and your little base, or the base of the log, are the same, you can cancel them out. So here, when it says find the exact value of each logarithmic expression without using a calculator, I can take a look at this first one and go, okay, this is log base 5 of, can I change 25 into something base 5? Yes, we can change that into 5 squared. I'm going to go, oh, hey, look, my big base inside my argument and my little base of the log are the same. So I can cancel them out. Now, when I cancel those bases out, this little base of 5, or the 5 for the log, is attached to the log. So the log also has to go away. And we just get our exponent. That's what we're left with. So if we tried problem D, I look at this and it's like, oh, it's already this little base of the log and the big base inside the argument, those are already the same. We're just going to cancel those out. We're left with an answer of -2. So feel free to take a look at the notes and go through and try all of these. I'm just going to try a few more, and then we'll move on to the next page. So if we move down to problem C over here, log base 4 of 1. So I had to figure out how to write 1 as a base of 4 so it'll cancel out. Well, just a reminder, anything to the power of 0 is 1. So I can write this as 4 to the power of 0. And then our big base and our little base are the same. We can cancel those out. And I'm just left with 0. If I try this for problem F, I see that we have a square root here. But remember, square root is the same as 1/2. So this is really log base 6 of 6 to the power of 1/2. We can cancel out big base and little base, and we are just going to be left with 1/2. And then lastly, if we try I take a look at this and I go, log of 1 over 10. Well, I know this log has a little base of 10, but 1 over 10, how do I write that as just a base of 10? Oh, I'm going to write this as log base 10 of 10 to the power of -1. I'm using my negative exponent rule. And once I do that, I can cancel out my bases and get an answer of -1. So since we're using logarithms, it means we're probably going to be using some more of our exponent rules as well. So make sure that you keep practicing those. I'm going to leave a few of these for the Go formative. I'll leave the rest for you to try on your own. Let's go to the next page. So on the next page, we get into E. Now, we talked about E a little bit in our last unit, and we're going to deal with it a little bit in this unit. I wish we can spend more time on it. But up here, it goes into more of like the calculus definition, and it even says somewhere on here, look at the graphs. Oh, maybe it's on the next page. Oh, no, it's right here. In calculus, you will study that the special properties of E is that the slope of the tangent line at 0 is exactly 1, as shown in figure 2. That's going to make a lot more sense next year when you were in calculus. But basically, E can be written as 1 over just a bunch of factorials. The factorial is the thing with the exclamation point. For instance, 5 factorial is 5 times 4 times 3 times 2 times 1. It's just being multiplied to all the things previous. We have a little graph over here. Oh, look at that asymptote. Interesting. We know that, I think we said this last time, right here, E is about 2.71 or 2.72. So we know it's going to be between 2 to the x and 3 to the x. It's going to be kind of in between there. But I wanted to show you that you can use E to solve just like we were doing previously. So if we take a look at example 5 over here, we can say, hey, look, e to the power of 3x is equal to e to the power of 2 minus x. Hey, look, both those bases are the same. We can set those exponents equal to each other and start solving. So I'm going to add x to both sides, divide both sides by 4, and get x is equal to 1/2. Still going to write my answer in a solution set, But I do this to remind you that e is not a variable. E is a number. And in fact, when we use it with logarithms, it has its own special representation called a natural log. So the natural logarithmic function is the logarithmic function with the base of e. So it says here log base e to the x. We don't really use logs when dealing with e. Log base e to the x, we call that ln base e. In case you are curious, it is called a natural log, but we use ln because of the French translation. I found that out last year. So if you see ln or natural log, that's going to have base of e. Just like a log without a base is a base of 10. So let's try doing some rearrangements here dealing with e. So let's do example 6. So 6 for a, we see here, okay, we're still going to want, base exponent answer. We're still going to want to turn that into log bay, except now instead of log, it's going to be natural log. So that's going to be natural log base e of, I started writing a, 7 is equal to x. So this is your base answer exponent or log or natural log of bay. But again, this is base e, and even if we don't see that base, we assume it's that base. So we can just say natural log of 7 is equal to x. If we try this with the next problem, problem b, if we do base exponent answer and we try to rearrange this, we'll get natural log base e, but you don't have to write that, 4 is equal to 2x. So we're taking the whole exponent and setting it equal to the problem, but we still have to continue solving. So we're going to divide the whole thing by 2, or I'm just going to say it's times 1/2. So 1/2 natural log of 4. So you're going to still use all the same rules for natural logs that you would for a log. It's just a different base. I just kind of wanted to talk about that for a moment. And just like we talked about the graph of e, we're also going to be taking a look at the graph of log base 2 to the x. Now, if we take a look here, if f of x is equal to 2 to the x, which we're very comfortable with, then f inverse of x is equal to log base 2 of x. Inverses. Yes, interesting. So it says sketch a graph of y is equal to f of x, and we actually already have that here. So I'm going to fill out this table for us real quick. So if here we have a table for 2 to the x, we actually already know a lot of it. We know 4, 2, 1, 1/2, 1/4. I'm just going to fill in the rest of these. If we have 2 to the power of 3, that's going to be 8. If we have 2 to the power of negative 3, that's going to be 1/8. And if we have 2 to the power of negative 4, that's going to be 1/16. So those are kind of all the pieces that you can see right here. So this is going to be 2 to the power of x. Now, just like it mentioned, log base 2 to the x is the inverse of 2 to the x. So remember, when we're dealing with inverses, that's you're going to switch your x and your y's. So you'll notice that for table 2, all of the y values that we just came up with are now the x values, and we'll say that all of the x values from our original table, or table 1, are now going to be all of our y values here. So if that's true and we graph all of these points, it should look like a reflection over the line y is equal to x. Let's see, that's -1. This is going to get really close. So it's going to look something. Ooh, really close. Whoops. It's going to look something like this. We can see it's been reflected over this line. Y is equal to x. And something else we haven't put in as well is an asymptote. So if our asymptote for 2 to the x is a horizontal asymptote, that means that our asymptote right here for log base 2 to the x is going to be a vertical asymptote. So we change from an asymptote of y is equal to 0 to x is equal to 0 because we're switching our x and our y's. That's all we're really going to cover for graphing since we spent some time on it for exponential functions, but I just want to let you know all the same rules still apply. Let's practice some of that solving. So on our next page, we have 4 different problems. I'm going to leave A and B for you to do in the coformative. I'm going to do C and D with you right now. If we take a look at the instructions, if we take a look at the instructions, it says solve the following equations, list your solution set. So remember, use those curly brackets for your solution. So when I take a look at C right here, I go, okay, I can't change this stuff inside the argument or inside the parentheses into a base of 3, so I'm going to use my bacon and eggs, or my log bay rule. Log bay. I'm going to change this into base of 3, exponent of 2, answer of 3x minus 2. Okay, that's not too bad. And then we're going to solve. So let's see, just a reminder, this was base, exponent, answer. So this is going to be 9 is equal to 3x minus 2. Add 2 to both sides. 11 is equal to 3x. Divide both sides by 3. I get 11 divided by 3 is equal to x. Put that into a solution set. And we're done. So it's just kind of like the solving problems from the last unit. It's just the first few steps when you're dealing with the log things that may be difficult, but then it just becomes a regular solving problem. So let's try problem D. So I look at this and I go, oh, you know what? 36, I can change that into a base of 6. This is going to be log base 6 of 6 squared is equal to 5x plus 3. From here, I can cancel out my bases of 6. Remember, when I cancel out the big base and little base, the log has to come with the little base. So we're just left with 2 is equal to 5x plus 3. I'm going to subtract 3 on both sides. So negative 1 is equal to 5x. Divide both sides by 5, and I get negative 1 over 5 is equal to x. Put that into a solution set. Okay, not too bad. So we're just practicing a few of the rules that we've already learned. Let's practice just a little bit more. We have 4 more problems on the next page. Again, we're going to do 2 problems together, and then you'll do 2 problems in the coformative. We're going to do problems B and C together. So I'm going to take a look at problem B, and I go, you know what? This seems like a good candidate to use my log bay rule and kind of do some organizing, because I don't see any logs here, so I can't cancel anything out. But I can't have a base of 4e. So before that, I am going to divide both sides by 4. So I get e to the 2x is equal to 9/4. And now I can use my log base. So this is going to be my base, exponent, answer, and I want to rearrange this into BAE, or bacon and eggs. So this will be log base e. I don't have to write, oh, pardon me, natural log base e, because this is dealing with e that's going to have a base of e. So I don't have to necessarily write that in there, but you can if you want to. My answer, or my argument, is going to be 9/4. That's going to be equal to 2x. So from here, again, this was my base, this was my answer, this was my exponent. From here, I'm going to divide both sides by 2, or multiply both sides by 1/2, and get 1/2 natural log of 9/4 is equal to x. Cool thing is, that's as far as we can go. You don't have to go any farther than that. So I'm going to put that into a solution set. So not too bad, only a couple steps. Let's try it again. Let's try C. So if I take a look at C, again, I am going to try the bacon and eggs rule, or the log bay rule. So if we do that, this is going to be base, exponent, answer. We want this in the order of BAE, bay, or bacon and eggs. So this will be natural log base e. Again, you don't have to write that, but you can if you want to. Of 13 is equal to negative 2x plus 1. So again, this was base, answer, exponent. And from here, I'm just going to start solving. So let's see, we're going to have, we'll subtract 1 on both sides. So natural log of 13, or base e, if you want to put that in there as well. minus 1 is equal to negative 2x. I'm going to multiply the whole thing by a negative 1/2, or divide everything by negative 2. So let's see, negative 1/2 times natural log of 13 minus 1 is equal to x. From here, I'm going to take the negative 1/2 and distribute it inside here. I'm not going to multiply it to that 13 because the 13 already has the natural log being applied to it. So this will just look like negative 1/2 natural log of 13 plus 1/2 is equal to x. And that's as far as we can go. That's as simplified as I can get. So I'm going to just put this whole thing into my solution set. This is as exact as we can go. Please give me exact answers, no decimals. And there we have it for today. So in the next video, we'll be learning a lot more rules, but go check out the coformative and practice these that we've already learned.